Here is a practice problem. I made the problem. So I don't know if you remember this. It was a long time ago, but the MythBusters, you know the MythBusters, they had this myth about a rocket-powered car, and so they wanted to make a rocket-powered car because who wouldn't? And so the myth was that this rocket-powered car hit something and flew off and crashed into a cliff or something awesome like that. So they made a rocket-powered car, and they made a ramp, and they drove the rocket-powered car remote controlled. It hit the ramp, and they want to see what happened. It did break the ramp. Okay, so I want to use this as an example of calculating the net force on the car during this situation. So I came up with some numbers. I didn't use numbers from the show. I just kind of made them up. And I'll show you them in just a second. So 2,000 kilogram car, initial velocity of 52 meters per second in the x direction. The ramp is 30 degrees. So what's the magnitude of the final momentum? Let's assume it doesn't change speed. It just changes directions. That's an okay approximation. Yes, I know there's a rocket on there. How long was the car in contact with the ramp? And then I asked, what's the net force? And how's that net force, how does the rocket force, or how does the net force compare to the gravitational force? So let's get to it. I have it on paper over here. So I drew all the important stuff right here. Here's car in position 1, position 2. So this is right before it hits the rocket. So we know this vector. It's in the x direction. And so it's 5200 for the velocity. I want to find the momentum at the end, P2, so I need to find the velocity. So the first thing I'm going to do is to say that V2, the magnitude of V2, is equal to the magnitude of V1. It didn't change speed, but it did change direction. So I know this is the magnitude of V1, so it's just going to be 52 meters per second. So now let's draw this vector. Here's V2. I know the magnitude of it. I want to find the x and the y component if the angle is 30 degrees. So if this is 52, then this would be Vx, this would be Vy. And so I can use my normal trig stuff. So let's say cosine of 30. Cosine is defined as adjacent over hypotenuse. So that's going to be Vx over, I'm just going to call that V. Let's just call this V. So from that, I can solve for Vx. Vx is going to be equal to V cosine 30. So that's going to be equal to 52 meters per second times the cosine of 30. So let's do that with the calculator, because I have a calculator right here. Can you see? No, can't see. Right there. Okay. So I'm going to say clear. I'm going to say 52 times cosine of 30. And you'll notice I am in degrees mode, so that's good. Enter. And I get 45, let's just say 45 meters per second. Now we can do the same thing for the opposite side. I can say the sine of 30 is equal to V y, opposite over hypotenuse, over V. So Vy is going to be equal to V sine 30. So it's going to be equal to 52 sine 30. And that will be equal to, I've got to put my calculator here. Can you see that? Nope, can't see it. Right there. 52 times sine 30 equals, and I get 26. So that gives my velocity vector V2 as 45, 26, 0 meters per second. Now what about the momentum? P2 is just going to be the mass times V2. So all I have to do is multiply both of these by 2,000, and I get my momentum. So let's do that. So I'm going to say, oops, clear. And the first one was 45, so it's going to say 2,001, 2, 3 times 45. And that's, 90,000. So let's say 9 times 10 to the 4th, and then clear 26 times 2, 1, 2, 3 equals. And that's 52,000, so 5.2 times 10 to the 4th, 0, and that would be kilogram meters per second. So that's the first thing. That's the first part of A. And now let's go ahead and get P1 also. So P1 is the momentum at the beginning, and that's just going to be equal to 52 times 2,000. And that's going to be, let's say 10.4. I'm going to write it as that. 10.4 times 10 to the fourth, 0 kilogram meters per second. Okay, so that's important. That's A. And all we had to do was use a little bit of trig right there. And we did make some approximations that the magnitude of the velocity didn't change that much. I mean, it would change if there's a thrust force and it's moving up, but we don't have to, it's a very short time. So let's just assume that is not the case. That is fine. Okay, now on to part B, delta t. How long was the car in contact with the ramp? Well, I did give in the thing, I said the ramp was 5 meters long. And I just made that up. So let's just call this the x prime direction for right now. I'm going to call this x prime. Oh, not x prime. X prime. And so I have a car going here, up there. Now, it's kind of tough, right? Because it's not really changing momentum during this time. So this is kind of a strange calculation, but it's fine. If the ramp was curved, then this would be a better approximation. But still, in this direction, Vx prime is going to be equal to 52 meters per second. Delta x prime is 5. So I can say Vx prime, just because it's in the new direction, is delta x prime over delta t prime, delta t. Now I can solve for delta t. You can't do this as a vector because I don't want to divide vectors by vectors. So I can say delta t is equal to delta x prime over Vx prime. And now I just need to put that stuff in. So I'm going to say clear. My x is 5 divided by 52. And I get 0.096 seconds. Why do I care about that? Because I want to estimate the net force. So this is part C. F net is going to be delta P over delta T, the momentum principle. So we can write that as P2 minus P1 over delta T. So P2 was the vector 9 times 10 to the fourth, 5.2 times 10 to the fourth, 0, minus the initial momentum, which was 10.4 times 10 to the fourth, 0. All of that divided by 0.096 seconds. So let's do the vector operation first. So if I take 9 times 10 to the fourth minus 10.4 times 10 to the fourth, I'm going to get 1.4 times 10 to the fourth, negative 1.4 times 10 to the fourth, right? Because that's 9, 1 more is 10, and then have the 0.4. You could do it in a calculator, that's fine. And now I'm going to take this minus that, and I just get 5.2 times 10 to the fourth, and then 0 minus 0 is 0. All of that divided by 0.096 seconds. So now I need to divide each term by that, and I'm going to get, let's do that in the calculator, right here. Okay, so I have let's do 1.4 times 10 to the fourth divided by 0.096. And I get 1.46 times 10 to the 5. And then I need to do 5.2 times 10 to the fourth divided by 0.096. And I get 5.42 times 10 to the 10 to the fifth, 0. And that's my net force. Okay, so the next question says, how does this compare to the gravitational force? Let's find the magnitude of this force since it's in two dimensions, but that's not super important. So I'm going to say F net magnitude. It's going to be this squared plus this squared square rooted plus 0. And so the 10 to the fifth is actually going to come out. I'm going to have 10 to the fifth, 10 to the fifth, and then I'm going to square both those, add them, and take the square root. So I can just find the magnitude of this and include 10 to the fifth. So let's do that. It just makes it a little bit easier. So it's going to be Can you see that? It's going to be the square root of 1.46 squared plus 5.42 squared, close parentheses, equals. And I get 5.61 times 10 to the 4th, 10 to the 5th. Yeah, newtons. Now let's compare that to the weight. mg, the magnitude, is going to be the mass, 2,000 kilograms, times 9.8, which is the magnitude of g. So that's not too hard. I can actually do that in my head, but I'm not going to because I'll make a mistake. 1, 2, 3 times 9.8 equals, and I get 1.96 times 10 to the 4th newtons. And so the point of this is that this is the total force. Do we really need it? What causes the change in momentum? Is it, or the force on the ramp, right? It's the force on the ramp is mostly due to the change in momentum, not necessarily due to the weight of the car, because this is 10 times more than this, more than 10 times more. So that's the thing. Now, like I said, this estimate of delta t is very, very, very large compared to what it would actually be, because the change in momentum goes from here, right before it hits the ramp, to right here once it's moving up, not the whole time up. But, it's made up a problem just for fun, and I thought that was fun. It's a good practice at using change in momentum with angles and finding the net force. So I hope that helps.